Welcome to the 36th lecture on computational mathematics with Sage Math. We shall continue exploring some more concepts on eigenvalues and eigenvectors. So, let us start with an example. Suppose you are given a matrix A, which is 4 by 4 matrix. Let us declare this in Sage Math. Next, let us find out what are eigenvalues of A. So, you can see here the eigenvalues of A are 4, minus 2, 2 and 2. So, 4 and minus 2 are appearing with algebraic multiplicity 1 and 2 has algebraic multiplicity 2. You can also find algebraic multiplicity of any eigenvalue using inbuilt method eigenvalue underscore multiplicity. So, for example, if I look at algebraic multiplicity of 4, it should give me answer 1. Similarly, if I look at algebraic multiplicity of 2, it should give me 2. Next, let us find out what are eigenvectors of A. So, eigenvectors of A are with respect to eigenvalue 4 is 1 1 1 1 and it is having multiplicity 1. Eigenvalue vector with respect to eigenvalue minus 2 is 0 0 1 1 and that is also of multiplicity 1, and eigenvectors with respect to eigenvalue 2, there are two eigenvectors with respect to eigenvalue 2, namely 1 0 minus 1 1 and 0 1 3 minus 1, and this is of multiplicity 2. Right. So, we can in fact find out this using another method called eigenmatrix underscore right. So, when you say A dot eigenmatrix underscore right, it gives you actually two matrices. One is this first matrix, which is nothing but the diagonal matrix with diagonal entries as eigenvalues. So, 4 minus 2 and 2 and 2, these are the 4 eigenvalues. So, that is the first output in this method, and the second one is nothing but the column vectors of eigenvectors corresponding to the eigenvalue. So, for with respect to eigenvalue 4, the eigenvector is 1 1 1 1 and that is what you see in the first column of this matrix. Similarly, with respect to eigenvalue minus 2, the eigenvector is 0 0 1 1 and that is the second column, and similarly with respect to eigenvalue 2, there are two eigenvectors. One is 1 0 minus 1 1, which is the third column, and 0 1 3 minus 1, which is the fourth column. So, let us store these output of A dot eigenmatrix underscore right in D and P. So, D is going to be this diagonal matrix of eigenvalues and A is the matrix of eigenvectors. So, this is D, this is P, right. Now, if you look at this P and you can check whether this P is invertible. So, I can say P dot is underscore singular, I should get answer false. This is not a singular matrix, this is a non-singular matrix, in particular P is invertible. Now, if P is invertible is same as saying all these columns are linearly independent. So, what it means is here these 4 eigenvectors that we have obtained for A, they are linearly independent, and in particular it will form a basis, that is what is called eigenbasis of A, right. So, let us find out what is A times P. A times P, P is this matrix of eigenvectors. A times P, what is A times P? The first column is 4 4 4 4, which is nothing but 4 times the first column, and 4 is the eigenvalue. So, it is the so first column is 4 times eigenvector with respect to the 4. Second column is 0 0 minus 2 minus 2, which is minus 2 times the second column of P. Similarly, the third column is 2 0 minus 2 minus 2, which is 2 times the third column of P. So, that is A times P. Now, let us multiply A times P by A inverse on the left hand side. So, P inverse A times P, then what you get? You get this diagonal matrix D, which is 4 minus 2 2 2. Okay, that was the diagonal matrix. So, here A dot eigen matrix underscore right results in two matrices D and P, such that P inverse AP is nothing but D. This is what is called diagonalizability of a matrix. So, this matrix is actually diagonalizable, and there is an inbuilt function to check whether something is diagonalizable or not. You can use is underscore diagonalizable method. So, for example, if I say A dot is underscore diagonalizable, then you will get an error. Let us see that this gives you an error. What it says? Matrix entries must be from a field, right? Whereas here the matrix entries by default it may be thinking of as an integer matrix. So, it is not in a field. So, it is possible that the matrix is diagonalizable, but your underlying field is not the appropriate one, then you will get false answer or you will get error. Now, let us change the field of A, that is change the ring, change underscore ring QQ bar. QQ bar stands for extended rational field, and then ask whether this matrix B is diagonalizable. The answer is true. We already know that this matrix is diagonalizable, and this P is called diagonalizing matrix. So, here P is diagonalizing matrix and this matrix is diagonalizable, right. So, now let us define formally what is meaning of diagonalizability. So, a matrix A, square matrix A is called diagonalizable if there exists a non-singular matrix P such that P inverse AP is diagonal matrix. Okay. So, already we saw that the matrix A is diagonalizable and P turned out to be the matrix of eigenvectors. Now, the next result is that if you have a actually this is a definition, if you have a vectors v1, v2, vn which are eigenvectors of A with respect to some eigenvalue lambda 1, lambda 2, lambda n, and also this v1, v2, vn forms a basis of Rn, then this basis, that is v1, v2, vn, is known as eigenbasis. So, eigenbasis is nothing but a basis which in which every vector is an eigenvector. Now, suppose you have an eigenbasis v1, v2, vn of A, then you define a matrix P to be the column matrix v1, v2, vn, that is take first column as v1, second column as v2 and so on. Then this, since this v1, v2, vn are linearly independent, P will be invertible. So, now if you look at P inverse A times P, that you can show that it is nothing but the diagonal matrix whose diagonal entries are eigen values with respect to eigenvectors v1, v2, vn. So, that is a very simple result and it is very easy to prove also. You can look at any standard book on linear algebra. Then the next result says that if you have an n cross n real matrix, then it is diagonalizable if and only if it has an eigenbasis. That is what it in the previous one it says, right. If you have an eigenbasis, it is diagonalizable, and the converse is also true. If the matrix is diagonalizable, then it is diagonalized using this invertible matrix P, then the columns of P will be eigenvectors. Another way of proving that a matrix is diagonalizable or not is to look at the geometric multiplicity and algebraic multiplicity. In case geometric multiplicity and algebraic multiplicity of every eigenvalue is same, then the matrix is diagonalizable. In fact, it is if and only if result. A matrix A is diagonalizable if and only if for every eigenvalue its geometric multiplicity is same as its geometric multiplicity. If algebraic multiplicity is same as geometric multiplicity. And in case you have got n distinct eigenvalues, one can show that eigenvectors corresponding to distinct eigenvalues are linearly independent, and if it has n distinct eigenvalues, then you will get n eigenvectors corresponding to each eigenvalue, and they are linearly independent. So, it will form a basis of Rn, and hence matrix A is diagonalizable. So, there are some of the simple results which tells you how when a matrix is diagonalizable, and not only that, how you can define or how you can diagonalize a matrix. Right. Now, let us take an example. So, let us consider this matrix A, which is again a 4 by cross 4 matrix. Now, if you find out eigenvalues of A, this has only two distinct eigenvalues, namely 1 and 2. 2 has algebraic multiplicity 3 and 1 has algebraic multiplicity 1. Now, if you look at the eigenmatrix of A, then the A, look at eigenspace of A. So, eigenspace with respect to eigenvalue A is one dimensional, because it has only one eigenvector, and eigenspace with respect to eigenvalue 2 is also one dimensional. So, that means algebraic multiplicity of 1 is same as geometric multiplicity of eigenvalue 1, but algebraic multiplicity of eigenvalue 2 is 3, whereas its geometric multiplicity is 1. Therefore, this matrix is not diagonalizable. This matrix is not diagonalizable. Now, let us look at another result. If you have similar matrices, how did we define similar matrices? To A, if you have two square matrices A and B, we say that A is similar to B if there exists a invertible matrix, let us say S, such that S inverse times A times S is equal to B. And in that case, if A and B are similar matrices, they have the same eigenvalue. So, let us just demonstrate this using Sage math. So, let us take a matrix A. This matrix, it has eigenvalue 9 and 2 and 2, only two distinct eigenvalues. Now, take any random matrix, let us say P, okay, and 3 cross 3 random matrix, and check if it is invertible. And once it is invertible, now let us define a matrix B, which is P inverse AP. So, that means A and B are similar. So, I will just print what is B. A and B are similar matrices. Let us find out what should be eigenvalues of B. Again, this is 9, 2 and 2. And if I generate once more this random matrix, now this time it is determinant is 0. So, P inverse AP will not have the, because inverse does not make sense. So, let us regenerate this. Now, this is invertible, and then you can look at B is equal to P inverse AP and find the eigenvalues of B. Again, it is 9, 2 and 2. So, it is actually quite easy to show that eigenvalues of similar matrices are the same, right. Next, let us look at an example where you can have same eigenvalues without matrix being similar, right. So, similar matrices have the same eigenvalues, but is the converse true? The answer to this is no. So, let us take an example. So, A is this matrix 1 1 0 0 1 1 0 0 1. This is a upper triangular matrix. So, upper triangular matrix, you can check that the eigenvalues of an upper triangular matrix is diagonal elements. Similarly, eigenvalues of a diagonal matrix will be the diagonal entries. Similarly, lower triangular matrix. So, this A has 3 eigenvalues 1 1 1, at only one eigenvalue with multiplicity, algebraic multiplicity 3. Now, do we know a matrix having 1 1 1 as an eigen value? Of course, we can take identity matrix. So, let us take B as identity matrix, 3 cross 3 identity matrix, and then the eigenvalues of B are also 1 1 1. Now, suppose if B is similar to A, then what would happen? There exists some matrix S which is invertible matrix such that S inverse B times S should be A. Now, what is S or let us say there exists a invertible matrix P such that P inverse BP should be A. But what is P inverse BP? B is identity matrix. So, P inverse BP is nothing but P inverse P, which is identity, and therefore, A is identity, which is not true. A is not identity. Therefore, this is an example of a matrix A which is similar to identity matrix, but A is a matrix and B is another matrix, both of them having the same eigenvalues, but they are not similar. Right. Let us look at what is advantage of diagonalizing a matrix. See, diagonal matrix will be the simplest matrix to deal with, right. So, in case you are able to diagonalize a matrix, many concepts will be very easy to explore. Let us look at one such. So, suppose A is a matrix which is diagonalizable matrix such that P inverse AP is a diagonal matrix whose diagonal entries are D1, D2, Dn. Now, let us take any power of P inverse AP. You can show that P inverse AP, when you take, let us say, square of P inverse AP, what will it be? It will be P inverse AP into P inverse AP. So, P inverse P and P inverse you can combine, make it identity. What you will be left with? P inverse A square P. So, in general, P inverse AP to the power k is nothing but P inverse times A to the power k times P. And since this is P inverse AP is diagonal matrix D, and power of a diagonal matrix is nothing but take power of each of these diagonal entries. So, that is the D to the power k. Now, this implies from this part you can find out what is A to the power k by multiplying this by P and then on the right hand side multiplying by P inverse. So, A to the power k is P times A D to the power k times P inverse. So, in order to find A to the power k, all you need to do is, once you have obtained this matrix P by which A is diagonalizable, you have to find D to the power k, which is simple. Finding power of any diagonal matrix is very simple task. So, that is advantage of finding power of a matrix, and this has lots of applications. So, before that, let us look at this matrix A and check whether this is diagonalizable. So, let us print D and P. This is the same matrix which we started with. So, this is diagonalizable matrix and P is the diagonalizing matrix, and let us find out this D to the power, let us say A to the power 20. What will be A to the power 20 by this result? It is nothing but P into D to the power 20 into P inverse. This is D to the power 20, not just 20. I can find out to the power 200. That's very large number, but in any case you can find it very easily. Let us say power 30, that is A to the power 30. And if you look at, is this equal to A to the power 30? Let us check this. Is it equal to A to the power 30? The answer should be true, right? Okay. So, that is one advantage of diagonalizing a matrix. It allows you to find any power of a matrix. Okay. Now, let us look at an application of this diagonalization, right. Let us look at this problem. Suppose a university campus has, let us say, 4 cycle stands, and they have 5,000 cycles located at 4 locations, and based on some past data, the various fraction of cycles that are taken from one place by the student dropped on another place, the fraction is given under this by this table. So, let me explain what it means. So, this this table means that 1/5 of the cycle hired from location A are dropped at location A, 1/10 from B dropped at A, 1/10 of cycles hired from or taken from location C are dropped at A, 3/20 of cycle that are hired from location D are dropped at location A. So, this is end of the, let us say, day. So, in the morning you have some cycles, and 1/5 from A comes at A, 1/10 from B comes at A, and so on. So, this is the matrix, and you can check here. In this case, the sum of the first column will be 1, sum of the second column is 1, sum of the third column is 1, sum of the fourth column is 1. So, that means the taxi hire cycles taken from A, all these things should be back to A, B, C. It is not dropped at some other location. That is where we are not considering, right. So, now let us look at how we can. So, the question is, suppose 5,000 cycles are there. So, how should one place these cycles at each location, so that in long run the students or whoever wants to hire take these cycles should be able to find at least one in whichever location he or she goes, right. So, this process should be smooth, right. Now, let us look at. So, if I look at the fraction of cycles that are that comes back at A will be, suppose you have x1 at A, x2 number of cycles at B, x3 at C, x4 as at D. So, x1 times 1/5 will come at A, x2 times 1/10 will come back at A, 3/10 of x3 will come back at A, and 3/20 of x4 will come back at A. So, total number of cycles at A after one day will be this. Similarly, you can find out total number of cycles after one day at B is this, and total number of cycles at C at after one day is this, and so on. And this 4 equations, 4 expressions can be written as a matrix multiplication of this matrix A by x1, x2, x3, x4, right. So, this is, suppose I call this matrix as A times the column vector x1, x2, x3 is the number of cycles that comes back at A. Now, these are the, suppose I call this as x1 dash, x2 dash, x3 dash, x4 dash, that is after one day. Then next day will be A times x1 dash, x2 dash, x3 dash, x4 dash, which is nothing but A square times x1, x2, x3. So, that is how you can find after 2 days, after 3 days, after n days, number of cycles that will be at various locations should be equal to A to the power n times x1, x2, x3, x4. So, you see that in long run, if I want to find this, I need to find the large power of A. Now, you just imagine instead of this distributing cycle in a university campus, suppose you want to do this in a big city. Then in big city you may need 1000 let us say some few thousand stands, right, and then the matrix that you will be dealing with will be, let us say, if there are 1000 stands, 1000 cross 1000. Finding power of a 1000 cross 1000 matrix even to a computer is quite expensive. Computer will also not be able to do it efficiently. So, that is where this diagonalizability will help. If you can diagonalize this matrix, finding any power of this matrix will be very easy. Now, of course, when you find diagonalize, you have to diagonalize using eigenvalues. Now, finding eigenvalues of 1000 cross 1000 matrix, you need to deal with polynomial of 1000 degree, which again is a difficult task. So, that is where numerical method comes into picture. So, you have to find these eigenvalues numerically. So, numerical analysis or numerical methods will be useful in this case. So, let us see how we can solve this problem. So, let us declare the matrix A as this matrix, which is first row is 0.2, 0.1, 0.3, 0.15 and so on. So, this you can check that sum of each column is equal to 1. In fact, in this case you can also show that in case you have sum of each column of a matrix as 1, then 1 will be an eigen value. So, and let us say the initially the distribution of cycle is 1000, 1000, 2000, 1000. So, at location A you put 1000 cycles, at location B another 1000, at location C 2000 and location D 1000. So, after one day how many cycles will be there at each location? That can be obtained by A times this initial vector V naught. So, after one day the distribution of cycles is something like this: 1050 at first location, 1450 at second location, 1000 at third location, 1500 at fourth location. After second day, so that means you need to find A times the distribution on at each location after one day, which is same as saying A square times V naught. So, after 2 days the distribution of cycles have become like this. Of course, it is possible that you might get this fraction value, in that case you have to round it off, and after 3 days A to the power 3 times V naught, this is the distribution. After let us say 20 days, what will be the distribution of cycles, and it says that it is going to be let me come down 842.5 to 1387.29 at B, 798.41 at C and 1971 at D. Now, instead of 20 days, suppose we find out at 200 days, after 200 days, then it is almost very similar to what you got after 20 days, right. So, again you can see here, now this is going to be very much stable. This is what is called a stationary vector. So, let us see what happens after, let us say not just 200 days, but let us say after 2000 days. 2000 days, again you can see here, this is almost very, so it very similar. So, it is actually converging to some fixed vector. So, that means if I have these many cycles at all these locations, then next day will also be almost similar. So, that means this process will run smoothly. Now, this is what is called a forecasting problem, and there are various types of forecasting problems. So, for example, you can look at migration problem, or let us say even Google search is very similar to this. And so, you can see here this is actually a real life problem, and in which you may have to deal with very matrix of very large dimension. So, 1000 by 1000, or if you are dealing with, let us say Google search, it will deal with all the websites that are connected to each other. That is a million of websites. So, you may have to deal with million by million matrix, and in that case you cannot find power of a matrix, and the only way to do is using diagonalizability concept, and that means you need to find eigenvalues, eigenvectors, but finding eigenvalues, eigenvectors is of a very large matrix is not an easy task, it is quite expensive. So, you may have to appeal to numerical methods. Okay. So, we will actually look at some more applications of diagonalizability also in solving system of ordinary differential equations sometimes later. This has got numerous applications. So, let me at the end also look at this. If you have a real matrix, then it is always diagonalizable. So, for example, if I take any matrix A, let us say this is a 4 cross 5 matrix, and suppose from this I want to generate a symmetric matrix. How do I generate? I can take A into A transpose, let us say matrix B. This B is going to be a 4 cross 4 matrix. Now, this is symmetric matrix, or you could have taken B A transpose A, that would have given you 5 cross 5 matrix. And then let us find out eigenvalues of B. These are the all real eigenvalues. Here actually you can see here, this is question mark, means this is approximate eigenvalue. So, it has computed eigenvalues numerically. That is what I said, that if you want to deal with arbitrary matrix, finding eigenvalues explicitly in closed form will be a difficult task, but then you need to appeal to numerical analysis to find eigenvalues numerically, right. So, now if you look at whether B is diagonalizable or not. So, let us change the ring of B, convert this ring, the underlying field from which the entries are taken, to QQ bar, extended rational field, and then check whether B is diagonalizable. The answer is true, and this you can do it with any matrix. Let me generate another random matrix, and this is B, and let us find out what are eigenvalues. And one thing you should notice here, that all eigenvalues of this B are non-negative actually. For example, instead of A transpose A, if I look at A transpose times A, this will be 5 cross 5 matrix. Now, if you look at eigenvalues of B, then one of the eigenvalue should be very close to 0. This is one of the eigenvalue is 0, and you can check whether this matrix is diagonalizable or not. So, this is diagonalizable. So, it is actually easy to show that any real symmetric matrix is diagonalizable, and not only that, you can define the matrix P which diagonalizes, and you can show that the columns of P will be orthogonal. The eigenvectors with respect to distinct eigenvalues of a symmetric matrix will be orthogonal. Okay. Now, let me leave you with a few exercises. First, look at this matrix A, diagonalize this. Then next matrix is again this 4 cross 4 matrix, and find the algebraic and geometric multiplicity of A and check if it is diagonalizable. And the next problem is find again algebraic and geometric multiplicity of each of this eigenvalue of A and check whether it is diagonalizable. So, this is again simple exercise, and the last one is look at this matrix A. So, this matrix again, the sum of the each column is 1, and each entry is non-negative. Such matrices are also known as stochastic matrix. So, if you have stochastic matrix, and in which case your sum of eigenvalues is equal to 1, you can take any power, or look at the large power of A, you will see that it converges to a matrix, a constant matrix. In fact, each column will turn out to be eigenvector with respect to eigenvalue 1. As I already said, if you have a stochastic matrix, it always has 1 as eigenvalue, and you will get an eigenvector. That is what we saw in case of this cycle distribution problem. Okay, so try to solve these problems. It is quite easy. Of course, we will be posting solution of these problems as well. Thank you very much.